Alright guys, for our 4.5 notes, we're going to be making some flashcards. So I just went and I got some blank printer paper. You can get blank paper or lined paper or scratch paper, just whatever you have lying around. And then I folded it in half twice. So folded it in half and then folded it in half again so that I had 4 quadrants on my paper. And then I cut them out. Or you can, get fancy and tear them or use a paper cutter. Whatever you want to do there, but you are going to need, so we're going to need at least 10 flashcards here, and then if you have a couple extra, there's a couple more that we can make. But go ahead and pause the video and make those flashcards real quick. Again, you're going to need at least 10. So pause this video and make those flashcards, or get them ready to go. Okay, so what we're going to be doing is we're going to be writing down the theorems that we have in this unit, theorems that we can use in our proofs. So the first one that we're going to do is the triangle midsegment theorem. So the triangle midsegment theorem, we already wrote down in our notes. So write it on one side, triangle midsegment theorem, and then on the other side, we're going to write it down. So triangle midsegment theorem states that if a segment joins the midpoints of 2 sides of a triangle, then the segment is parallel. We know this about our midsegments. Parallel to the third side, the one it doesn't touch, and is half its length. Okay, so then we're going to go ahead and draw a midsegment. So we're going to draw a triangle. I got a ruler out. I would say use a straight edge at least. Side of your ID card. Side of the binder. Okay, use a straight edge. Make it look good. Okay, so we've got a triangle. And I'm going to go ahead and call this triangle ABC. And then we're going to put midpoints on sides A, AB, BC, and AC. And I'm going to call those midpoints D, E, and F. So each of these would be midpoints if we knew that their halves were congruent, or if we were told that they're midpoints. Then between each of these, we have a midsegment. So if I connect E and F, that's a midsegment. If I connect D and E, also a midsegment. And then D to F is the third midsegment. So every triangle has 3 midsegments. Okay, and then according to the triangle midsegment theorem, each of these midsegments is parallel and half of its third side. So for example, DE is parallel to AC. It will never intersect it. And DE is also half of AC. Also, EF is parallel to AB and is half of AB. And then our third midsegment, DF, is parallel to BC and is half of BC. So there is a good lot of information in this flashcard for the triangle midsegment theorem. Okay, so that's our first flashcard. Second flashcard, second theorem, and go ahead and pause the video wherever you need to make sure that you're not falling behind here. Okay, so second theorem is going to be called the concurrency of the perpendicular bisectors, which we've talked about, right? Perpendicular means it intersects to form a right angle. Bisectors means it cuts it in half. So we have the concurrency of the perpendicular bisectors of a triangle theorem. So long title, concurrency of the perpendicular bisectors of a triangle theorem. Like the grammar isn't right here. So then we're going to define it on the back. And the definition of this theorem is that the perpendicular bisectors of a triangle intersect at a point that is equidistant. That's a word we've seen before, right? Equidistant means equal distances. Equidistant from the vertices, aka corners, right? Vertices of a triangle. Okay, so then this point that it intersects at, well, here, we'll draw our triangle. So let's draw triangle ABC again. And then we're going to draw perpendicular bisectors. So my perpendicular bisector needs to make a right angle here. And go ahead and actually change my color. So it needs to make a right angle and go through the midpoint of that side. So there's one. And my perpendicular bisector for this side. And I'm just eyeballing this here, making it, trying to do my best to make a right angle. There's two. And then three. Okay, so what we can see here is that these three perpendicular bisectors intersect at this point here and this point. So they should, you know, if you do a pretty good job making right angles and drawing through the midpoints, then they should at least get close to the same intersection. And if we did it more accurately, they would intersect at a definite point. Okay, but that point, we'll call it H. Okay, H is what we call a circumcenter. 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 So we talked about with medians where they intersect is called the centroid. We talked about where altitudes intersect is called the orthocenter. So where perpendicular bisectors intersect is called the circumcenter. And what we need to know about the circumcenter, besides that it's where the perpendicular bisectors intersect, is that it is equidistant from the vertices. Okay, so that means that point H here is the same distance from C as it is from B as it is from A. So HC is the same as HB is the same as HA. So that circumcenter there, that point where it intersects, is the same distance from A, B, and C. Okay, so our perpendicular bisectors intersect at the circumcenter, and the circumcenter is equidistant from the vertices of the triangle. Okay, so there's our concurrency of the perpendicular bisectors of a triangle theorem. Okay, second flashcard. Okay, now we're going to do the concurrency of the angle bisectors of a triangle. So we just did perpendicular bisectors. Now we're going to do the concurrency of the angle bisectors. So this one is concurrency of the angle bisectors of a triangle here. Okay, and this theorem states that the angle bisectors, so we talked about angle bisectors, they are segments that cut an angle in half. So the angle bisectors of a triangle intersect at a point Oh, and I guess I was telling you guys to make flashcards earlier, but if you have flashcards, you can use those too, of course. Okay, so these intersect at a point that is equidistant again, equal distances from the sides of the triangle. So the perpendicular bisectors bisect the sides, but are equidistant from the angles, the vertices. The angle bisectors bisect the angles and are equidistant from the sides. So we're going to draw what that looks like as best we can here. Okay, so we're going to get triangle ABC on there again. Okay, so triangle ABC. Now this we have to bisect our angles. We have to try to bisect our angles. Whoop, lost my light here. Go. So to bisect the angles, you got to try to split the angle in half. It's going to be a little tougher. So do your best. Let's see how we can do here. I'm going to try to make two equal halves. So that was not great. Let's see if I can do a little better on C. A little better. And I'm just going to make sure I angle B right through here because my angle bisectors are supposed to intersect at a point. Okay? So, your angle bisectors, now we'll show that they are angle bisectors. We're going to go ahead and mark that all of the angles that they cut are congruent or split into two equal halves. So C we'll say is bisected, A is bisected, and B is bisected. Okay? And then we can see that our angle bisectors also intersect at a point. Okay? And that point is called the incenter. So we'll call that point P, and P is what we call an incenter. So we have our centroid, our orthocenter, our circumcenter, and our incenter. And all of them have that word cent, which implies concurrency. So it's kind of like currency, it means money, and money is cents, right? All of these words, all of these points of concurrency are centers or centroids. So some interesting literary vocabulary connections there. Okay, but then according to our theorem here, our incenter is equidistant from the sides of our triangle. So that means that P here is the same distance from AB. Now distance is always has to be measured with a right angle to show that it is the shortest distance. Okay, so P, and again it's not a perfectly drawn picture, okay, but P would be the same distance from side AB as it is from BC as it is from AC. So if I named these points D, E, and F, just to show that, okay? And those are not, again, those are not necessarily the midpoints of those sides. They're just the closest point on those sides. Then PE would be the same as PD, would be the same as PF. So the end center is the same distance from the sides of the triangle. And we know this is the end center because these segments going through a triangle are angle bisectors. Okay, so that is the concurrency of the angle bisectors. And those are the longer ones, so hopefully we can go a little faster through some of the other ones here. So the next one is the centroid theorem, which again we've already written in our notes. Okay, the centroid theorem states that the centroid, which is where medians of a triangle intersect, so the centroid is 2/3 of the distance from each vertex to the midpoint of the opposite side. Okay, so again, we're going to draw a picture. And this time we're going to draw our medians. Medians go from a vertex to a midpoint. So we've got triangle ABC. And then I'm going to draw my medians. So I'm going to make my midpoints on the sides as best I can, putting those points in the middle. Okay, and then I'm going to go from the vertex to the midpoint for each of these sides. So vertex to midpoint. And vertex to midpoint. And vertex to midpoint. Again, I did a pretty good job with my midpoints there because my medians get really close to intersecting at the same spot here. So this point where they intersect, I'm going to go ahead and call it point Q. Okay, Q we know to be the centroid. And we know that BQ, B to Q, is 2/3 of B to, we need a point here, we'll call this P. Okay, so B to Q is 2/3 of B to P, and B to Q is 2 times Q to P. And we could also say Q to P is 1/3 of B to P. Okay, so a couple different ways to set up these types of problems. So each of these little midpoints, so same thing, right? A to Q is 2/3 of A to, let's call this M. And A to Q is 2 times Q to M. And Q to M is 1/3 of A to M. So again, all these different relationships that exist on these centroids, or on these medians. Okay, And then a median, again, goes vertex to midpoint. So median goes vertex to midpoint. Okay, so there's our centroid theorem again. Then we're going to do the angle bisector theorem. So the angle bisector theorem is one that we already wrote down as well. The angle bisector theorem states that if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So if we have an angle and again, you guys, we are making these flashcards so that you can use them to study for your test, which is next week. So you can quiz yourself on what these theorems are, what you know about each of these pieces. Right? What do you know about the centroid? What do you know about the perpendicular bisectors? Okay, so if we have an angle bisector, okay, BD, if we know that BD is the angle bisector here, then we would know that D is the same distance from this side of the triangle as it is from this side of the triangle, angle. And again, those distances have to have those right angles there to show us that it's the shortest distance. So if we don't have the right angle here, then we don't know for sure that it's the shortest distance. So this length would be equal to this length. So the red here is what we know, and the green is then what we can infer based on what we know. Because then on the converse idea, we're going backwards, right? So the converse of the angle bisector theorem is that instead of knowing that it's an angle bisector, so then being able to conclude that these are congruent, the converse of the angle bisector theorem is that if a point is in the interior of an angle, and is equidistant, equal distances from the sides of an angle, then it lies on the bisector of an angle. So again, we're going to do the red is what we know, the green is what we can infer, so we're going to draw an angle again. We have angle ABC. Okay. If we have a point out here and we know that that point is equidistant from the sides of our triangle. So again, if we know that these distances are the same, then what we can infer, what we can conclude, is that D is on the angle bisector of this angle. So again, red is what we know, green is what we can conclude. So if we know that D is equal distances from the sides, then we know that it's on the angle bisector. So see the difference here, right? Red, what we know, green, what we can conclude. In the regular one, we know it's on the bisector, so we can conclude that those distances are equal. And the converse idea, we know those distances are equal, so we can conclude that it's on the angle bisector. Okay, so then it's the same, guys, with the perpendicular bisector theorem. And I know these ones are a little longer, but we're making things that you can study for or study with. So it's good stuff, okay? So we're going to do the perpendicular bisector theorem. Now make sure that over this next week and a half that you have till your test that you are using these to study. You can quiz yourself, a couple each day, right? Study them. So the perpendicular bisector theorem states that in a plane, which just means that they're in the same realm of the universe. Okay? In a plane, if a point is on perpendicular bisector of a segment, because perpendicular bisectors bisect segments, angle bisectors bisect angles, then it is equidistant from the endpoints of the segment. Okay? So if a point is on the perpendicular bisector segment, then it is equidistant from the endpoints of the segment. So again, on this one, we're going to go purple is what we know, pink is what we conclude. Okay, so if we have a line segment, and we have what we know to be a perpendicular bisector, we'll call this MP. Okay, so if we know that this is a perpendicular bisector, which we do based on perpendicular and then these congruent halves, okay? So if we know that it's a perpendicular bisector, then AP is congruent to PB. So again, pink is what we can infer. AP equals PB. Purple, what we know, pink, what we can confer. Conclude. So then the converse idea, same thing. Okay, so if we know it's a perpendicular bisector, then those segments are congruent. And the converse idea is that if we know it's congruent, if we know it's equidistant, then we know it's on a perpendicular bisector. So the converse of the perpendicular bisector theorem states that in a plane, if a point is equidistant from the end points of the segment, then it is on the perpendicular bisector, of the segment. Okay, so again, purple what we know, pink what we infer. So in this one, if we have a segment, not a great segment, and I have a point, we'll call it C. Okay, if I know that C is the same distance from B as it is from A, again, if purple is what I know, C is the same distance from B as it is from A, then pink, what we can conclude, oh, this picture is not drawn great, okay, but pink, what we can conclude is that C is on the perpendicular bisector of the segment. So purple, what we know, pink, what we can conclude. So, right, we got our two differences here, okay? First one, perpendicular bisector theorem. If it's on the perpendicular bisector, then we know it's equidistant. Converse idea, if we know that it's equidistant, then we know it's on the perpendicular bisector. Okay? Alright, bear with me guys, we're almost done here. Okay, last thing we're going to talk about, and so actually I think we're just going to do 9 flashcards, my count's right here, is altitudes. Because we already talked about centroids, perpendicular bisectors, angle bisectors, and midsegments. The last piece of the triangle that we have been working with is the altitude. So altitude is the height of a triangle. It is a perpendicular segment from a vertex to the line containing the opposite sides. The opposite side. So altitudes go vertex to right angle. That's how I wrote it, okay? Altitudes, you guys, can be inside the triangle, on the side of the triangle, or outside the triangle. Okay, and then altitudes, as we kind of mentioned in our 4.3 assignment, is they intersect at what's called the orthocenter. So we have centroid, again, all these points of concurrency, centroid, circumcenter, end center, and then here's the orthocenter. So we're going to go ahead and attempt to draw our altitudes intersecting at the orthocenter. We'll see how it goes. So altitudes always go vertex to right angle. Medians go vertex to midpoint. Perpendicular bisectors go through the midpoint at a right angle. Angle bisectors cut the angles in half. The altitudes go from vertex to right angle. So I'm going to draw 3 altitudes here that go from my vertex to a right angle on the other side. So if I go A to right angle here, it looks something like that. If I go B to right angle, something like that. And depending on how well I do my right angles here, these should all 3 intersect. So C to right angle, looks something like that. Okay, so there's my 3 altitudes in my triangle. And this point where they intersect, we will call it R. Okay, that point R is the orthocenter. Okay, and that's pretty much all we know about the altitudes of the triangle. All right, so altitudes intersect at the orthocenter. Perpendicular bisectors intersect at the circumcenter and are equidistant from the angles. Angle bisectors intersect at the incenter and are equidistant from the sides. Medians intersect at the centroid, which are 2/3 of the distance. So the centroid is 2/3 of the way from the vertex to the midpoint. And then a couple of other ones that we talked about, right? We did the triangle midsegment theorem. Midsegments are parallel to their third side and half the length. I think that was my least colorful flashcard here. Then we had the angle bisector theorem. Again, what we know, red, what we can conclude, green. So if we know it's on the angle bisector, then we can conclude that it's equidistant from the sides. Versus the converse idea, which if we know it's equidistant from the sides, then we can conclude that it's on the angle bisector. Similarly, perpendicular bisector. We know it's on the perpendicular bisector, then we can conclude that it's equidistant from the endpoints. And the converse idea, we know that it's equidistant from the endpoints, then we know it's on the perpendicular bisector. So again, you guys, a lot of good stuff here. I know this was a little long, but use these, okay? You got a week and a half, study these. If there's anything else from this unit, any other vocab in particular that is giving you trouble, then you got a couple extra flashcards that you could make. Alrighty, good work, team.